as we move into Chapter 11, Section 1, we're going to be focusing on sequences and series, as well as induction in the binomial theorem. Now, hopefully, this is a lot of review stuff for most of you, either from college algebra, maybe your trig teacher covered it, you may have done some sequences and series stuff in high school, but it shouldn't be brand new. When you hear the word sequence, we think of this as a series of events, something that happens first, second, etc. In math, that also deals with outcomes that come in an order. By definition, a sequence is a function whose domain is our set of positive integers. So think of it as our domain is going to be the number of the terms. You have a first term, second term, third term, fourth term, etc. You don't have a 2.5 term, right? So it's going to be the set of positive integers. We're going to write the first several terms of this given sequence. So we have our general term, and then we have our rule to follow, and we want the first 6. So we are going to do a sub 1 to a sub 6. So let's set that up. We have a sub 1, a sub 2, a sub 3, and then I'm going to come over here and do a sub 4, a sub 5, and a sub 6 to represent our 6 terms. Now for each term, I take the number of the term and square it for my numerator, and I do 2 times n plus 1 for my denominator. So where I have the first term, I have 1 squared, which is just 1, over 2 plus 1 is 3. For my second term, I have 2 squared, which is 4, over 2 times 2 plus 1 is 5. For the third term, I'm going to have 9 over 6 plus 1 is 7. For my fourth term, I have 16 over 8 plus 1 is 9. For my fifth term, I have 25 over 10 plus 1 is 11. And then for my sixth term, which is the last one I was asked to do, I have 36 over 13. Now, you can see that these are progressing. I start with a proper fraction of 1/3, and I've ended up here at 36/13, which is almost 3, not quite 3. But can you see a pattern? Well, there's a clear pattern in our denominator. We're adding 2 each time, but it's hard to find a clear pattern in our numerator. So let me give you a suggestion. Let's plug these into our calculator. If we plug them into the calculator and round to 1 decimal place, 1/3 is about 0.3, right? If I plug in 4/5, I get 4 divided by 5 gives me 0.8. And what about 9/7? Well, 9/7 comes out to be 1.3, and then I have 1.8. Now do you see a pattern? Well, I have a common difference between each successive term. I'm adding 0.5 each time, so I don't have to plug these next 2 in, do I? I can just say, you know what, then I'm going to have 2.3, and then I'm going to have 2.8, and then I would have 3.3, and I could just keep going. If I wanted to graph these, let's say I want to put these on a graph. Well, my x-axis is going to be the number of the term, so I just need positive integers on my x-axis. 1, 2, 3, 4, 5, 6. And then my y-axis, I could count by halves, right? I could say, okay, so let's do 0.5, 1, 0.5, 2, 0.5, 3. So this would be 0.5, 1, 1.5, 2, 2.5, 3, and that gets us as far as we need to go. Now this is not going to be a continuous function. These are not continuous points that we are going to connect. We're just going to graph the individual values. So my first term is 0.3. That's going to be about right here. My second term is 0.8. My third term is 1.3. And you can see that I have a linear increase. And I've stopped paying attention. So if I did connect them, I could connect them with a line because it's increasing by a set amount each time. But it's not a continuous graph. These are discrete values. So we are not going to connect the points on the graph. It's not continuous, it's discrete. Okay, let's look at number 2. Write down the first several terms. Again, we're asked to give the first 6 terms of our sequence. So let's set this up. Now instead of A sub n, we have B sub n. So let's do B as our general term. So we have B sub 1, B sub 2, B sub 3. Can I squish that in? I think I can. B sub 4, B sub 5, and B sub 6. We're asked to find the first 6 terms. There we go. Now you can see. Where our general term is negative 1 to the n times 2 to the n. So for our first term, we have negative 1 to the first times 2 times 1. So we have a negative 2 for our first term. Now, anytime you see this negative 1 to a power, the whole purpose of that is to cause alternating signs. This causes alternating signs. So when I know whenever I see negative 1 to whatever power that it's either going to start positive and then go back and forth to negative, positive, or it's going to start negative and do the same thing. That means that for this term, this first term is negative, my second term is going to be positive, because when I plug in 2 for n, that's negative 1 squared is just a positive 1, and I have 2 times 2 is 4. So my signs are going to alternate, which means I really don't have to worry about this anymore because I know it's going to be alternating. This one's going to be negative because I have an odd exponent here. 2 times 3 is 6. This one will be positive because that will be an even exponent, and 2 times 4 is 8. That makes this, can you see your pattern here? Negative 2, positive 4. Negative 6, positive 8. This will be negative 10, and then a positive 12. These have a common factor. I'm multiplying by the same thing each time. If I wanted to go from one term to the next, I could just say, you know what, I'm just going to multiply. No, I'm not multiplying by the same thing each time. I take that totally back. I had in my head I was multiplying times 2 each time. I'm not. I'm adding 2 each time, aren't I? But I'm adding, it's positive, negative, so it's not an arithmetic function. Nope. Okay, I have an alternate question for you. Let me move away from that and give you an alternate question. What if I wanted my first term to be positive? How would I start with a positive first term and alternate? Well, to start with negative, I did negative 1 to the n. To start with a positive first term, I could say negative 1 to the n plus 1. Okay, let's look at our third example. Write down the first 6 terms of this sequence. Now, I have 2 different rules for this. Oh, you know what? It has 2 different ones here. This is a place where we've got another typo. Ignore this. This is the one we just did, right? That's the one we did up there. This is the one we're doing now. I have 2 different rules. I have a rule for when n is n is even, and a rule for when n is odd. But we're finding the first 6 terms. My general term is c sub n. So I'm going to have c sub 1 through c sub 6. There's not a magic anything to go with 6 terms. That's just what it gave us. Okay, so where n is odd, the number of my term is odd, it's just n squared. So 1 squared is 1, 3 squared is 9, 5 squared is 25. But where n is even, I just totally did this backwards, guys. Oh my goodness. Let's go back. Where n is odd, that's my second rule. Where n is odd, it's just n. So that should just be 5. Oh my word. I hope you're all at home yelling at me about that. Okay, where n is odd, it's just n. But where n is even, it's n squared. So 2 squared is 4, 4 squared is 16, and 6 squared is 36. At least I know how to square my numbers. I just couldn't follow the rules. Okay, so it gave me a general term c sub n, and it gave me 2 different rules depending on whether n was odd or even, and I managed to mess it up, but we got it fixed before we moved on, so that's a win. Okay, now this is a thing that I like to do in class with groups so that you guys can work together to figure this stuff out. Since we don't have a class to work in groups in, I'm going to encourage you to pause the video and take a look at these and see what you can come up with, and then start it back up and see what I came up with. Okay, we're going to add something to this. We're going to find our formula, and our formula is going to be in terms of a general term. Now, a general term is going to be a sub n, b sub n, or c sub n. Let's just use a sub n for these. After you found the general term, then I want you to find the 30th term. Find n equals 30, just so we know how to apply our general term. All right, hopefully you have done that. For this first sequence, a good general term would be a sub n equals 1 over 2 to the n, because these are all powers of 2. This is 2 to the first, 2 squared, 2 cubed, 2 to the fourth. My next exponent would be 1 over 2 to the fifth, which is 1/32. That's my general term. And then if n is equal to 30, I would have a sub 30 equals 1 over 2 to the 30th. Now if you plug that into your calculator, it gives up and switches to scientific notation, because 2 to the 30th is huge. So 1 over 2 to the 30th is tiny. If I do 2 to the 30th, that's what I get, right? So we have used almost every available spot in our calculator. So it would be 1 over that would be 1 over 2 to the 30th. So that one's a really, really big one. The rest of these are not going to be that big, not going to be that bad. Okay, so what about B over here? What about B? I have 5, 7, 9, 11. Well, when I look at that, I notice that I'm adding 2 every time. A good general term would look like a sub n equals 3 plus 2 to the n, because if I'm looking at my first term, a sub 1 would be 2 times 1 is 2 plus 3. This is my 1, 2, 3, fourth term. 2 times 4 is 8, plus 3 is 11. So a good general term is 3 plus 2 to the n, and this is an arithmetic sequence because it has a common difference between each term. What if I want a to the sub 30, my 30th term? Remember I said defined n equals 30. Well, then I just plug in 30 for n, and in this case I get 63 as my 30th term. Now I don't have to go through all 30 terms. I can just, when I have a good general term to work with, I can just jump to that 30th term. So it's good to have a general term that is not what we call recursive, where you depend on the term before it. All right, what about C? I'm just alternating ones here. So this one's a pretty simple one. I can do a sub n equals -1 to the nth power. We have a common factor here, common multiple, that -1. If I want a sub 30, that would be -1 to the 30th power, and because that exponent is even, that gives me a +1. And finally, this last one, this one's a little bit trickier. I have 2 different general terms for this. The first one is what we call recursive, where you have to know the term before. And this is one that one of my groups in class came up with. I was really, really proud of it. They said if we want to define it recursively, recursive definition for my general term, my first term would be 3, that's given. And then my general term from that is going to be previous term, a sub n minus 1, plus 2n minus 1, and that's good for all the other terms, for all n greater than or equal to 2. Now this works. This is an excellent recursive definition, general term definition. Another group came up with a general term that was not recursive. They said, okay, we can just do a sub n equals n squared plus 2. So this is the one that we want to use to find the 30th term. If we use a recursive defined general term, we have to find all 30 terms to get to that 30th term. To use this one, we just plug in 30 for n. So we have 30 squared plus 2, which 30 squared is 900, and that is 902. All right, so what do you think about that? And again, I started to say, any questions? I miss having a class full of students. Okay, so here we go, 0 factorial. We're going to talk about factorial on the next page, and we start by defining 0 factorial. So I actually pulled it up on the computer and thought about what is 0 factorial. So I want you to kind of read through this. Basically, 0 factorial is defined as 1 because it fits our pattern. The best way I like to describe 0 factorial is using permutations. If you do statistics, you know that permutation is a way of grouping objects or items or numbers, and in a permutation, order matters. If I have one thing, I can group it one way just by itself. If I have 2 things, I can group them in these 2 different orders. If I have 3 things, I can order them 6 different ways, etc., etc. If I have 0 things, I can order it one way. Nothing. There it is. So our 0 factorial fits our definition, our pattern for our factorials. And it's a good way to, it's just defined as 1. So it is what it is. 0 factorial is 1. 1 factorial is also 1. In factorial, I start with n and I multiply my way all the way down until I get to 1, as long as n is 2 or more. Hopefully you remember working with factorials from a previous course. 5 factorial is going to be 5 times 4 times 3 times 2 times 1, which is 120. 6 factorial would be 6 times 5 factorial, right? Because 6 times 5 times 4, 6, 5, 4, all the way down to 1, which is the same thing as 6 times 5 factorial. We just saw that 5 factorial is 120, so it would be 6 times 120, which is 720. These are some good ways to reason through some things. So n factorial is n times n minus 1 factorial. Now, this is helpful, for example, if you need to simplify something. If you need to simplify with factorials, for example, if I have 15 factorial over 13 factorial times 3 factorial, well, I can recognize that in my numerator, I just need to go down to this 13 factorial. So 15 factorial would be 15, 14, 13 factorial. Then in my denominator, I have 13 factorial there. And then I also have 3 factorial, which would be 3 times 2 times 1, right? Well, 13 factorial cancels out, and I'm left with 15 times 14 over 3 times 2. If I wanted to simplify further, I could. What I'm going to end up with is 35. Simplifying further, I could say, you know what, 15 divided by 3 is 5, 14 divided by 2 is 7, and 5 times 7 is that 35. But being able to recognize this helps us in cases like this one here. In other classes, I've given students problems like 103 factorial over 101 factorial. Well, you need to recognize that this is just 103 times 102 times that 101 factorial, and that cancels out. So all I actually have to do is multiply 103 times 102. Now let's look at your calculator for this factorial business just real quickly. You probably all already know this, but if I have a factorial button. If I go to probability, it's going to pull up permutations, combinations, and factorial. So I can move over. Whoops, don't want to move over that far. I move over to my factorial, hit enter. I've got 103 factorial, and it says, oh, that's too big. I can't calculate that. So that's going to give you the key that you do need to simplify here. I would go back and I'd say, okay, let's just do 103 times 102 because I've already canceled the rest out. So that gives me 10,506. But my reason here for pulling out the calculator was showing you that overflow error to encourage you to simplify where you can and to point out your probability button so that you know you can make use of that when necessary. Okay, another way to define sequences is to write them recursively. Now, we talked about recursively defined sequences on that first page, so you've already been introduced to that, reminded of that. This means we give you a value for the first term, or maybe the first 2 or 3 terms, and then describe the nth term, that general term, by a formula that refers to a previous term. So any time you see an n-1 subscript or n-2, anything like that, you know you have a recursively defined sequence. If it gives you a recursively defined sequence, it's not going to ask you for the 20th term or the 50th term. It's just going to ask for example, the first 5 or 6 terms. So let's do that. Let's do s sub 1, s sub 2, s sub 3, s sub 4, and s sub 5. I think I can squish all those in. My first term is given. It's just 5. My second term is 2 times the previous term. So 2 times 5 in this case is 10, previous term. Then I do 2 times previous term now is 10, so that's 20. 2 times previous term is 40. 2 times previous term is 80. So that my first 5 terms are 5, 10, 20, 40, 80. And you can see I'm doubling every time. If I wanted to do the 6th term, that's going to be 160. If I want the 100th term, that is a pain because there's no way to get there except to go through all of them. So we don't like that one. Okay, this one tells us to write the first 5 terms, and it defines the first 2. So it gives you u sub 1 and u sub 2, and you need to find u sub n plus 2. Our first 2 terms are given. First 2 terms are given, so that's nice. So we really only need to find 3 more. U sub 1 is 1, u sub 2 is 1, u sub 3 is n plus 2. So n plus 2 is going to be, this is 3. So this is going to be u sub 3 plus 2. I'm looking at this backwards. Where n is 1, okay, sorry guys, start over. So where n is 1, I've got u sub 1 plus 2, which is u sub 3, which is u sub 1 plus u sub 2, because n is 1. N is 1, n is 1, n is 1. So 1 and 2 are defined for me both as 1. So that's 1 plus 1 is 2. Where n is 2, I've got u sub 2 plus 2, which is u sub 4, and that's going to be u sub 2 plus u sub 3. U sub 2 is 1, u sub 3 is 2, so that's 3. Where n is 3, I've got u sub 3 plus 2, which is u sub 5, and that is u sub 3 plus u sub 4. The u sub 3 was 2, and u sub 4 is 3, so that's going to be 5. If we wanted to go on and just go ahead and do n equals 4 and n equals 5, we would have u sub 4 plus 2, which is u sub 6, which is going to be u sub 4 plus u sub 5, which are these 2 terms. 2 plus 3 is 5, 3 plus 5 is 8. And then for this one, 5 plus 2 is u sub 7, would be u sub 5 plus u sub 6, which is the 5 and the 8, is 13. So we were given the first 2 terms, we actually found the next 5. Okay, let's go to the next page. I didn't like getting confused on that one. You're not going to see very many defined like that, and very many recursive terms defined like that, I believe, unless they've changed the homework on me. Oftentimes we want to find the sum of the first n terms, so we're finding sums now. So far we've been focusing just on the series. Now we're going to find, we're focusing on the sequence. Now we're going to talk about a series, which implies that we're interested in the sum of the sequence. and we're going to use summation notation. Now this is my index, this is my summation notation where it's based on the Greek sigma, and that means sum, and the integer at the bottom, k in this case, it could be something else, is called our index of summation, and it tells you what term to start with and what term to stop with. So my lower index where I start is at the bottom, and my upper index where I stop is at the top. If the top is n, we have an infinite number of terms in our sequence. So this summation notation is read as the sum of a from k equals 1 to k equals n. So we're looking for the sum of an infinite sequence there, and that may not be possible to find. Now, for example 8, it tells us to use summation notation to write out each sum. We don't have to evaluate it. So we're not asked to actually find the sum, because some of these you can't find the sum if it's an infinite sequence. We're just asked to tell you how you would find the sum. So here's our general term, and we're interested in adding the terms from 1 to n. Well, our first term would be 1 over 2, because if k is 1, our denominator is 2. And then I'm going to add to that my second term, which would be 2 over 3, where k is 2. And my third term, which would be 3 over 4 if k is 3, and I'm going to keep going until I get to that nth term. If k is equal to n, I have n over n plus 1. So that represents the sum of this infinite series. Let's look at b. Once again, we're going to start this time though with k equals 0. So if k is 0, I have a negative 1. And I'm going to add to that, if k is 1, I have 1 squared minus 1 is 0, and I'm going to add to that. If k is 2, I have 4 minus 1 is 3, and I'm going to add to that. If k is 4, I have 4 squared is 16, minus 1 is 15. 0, 1, 2, 3. 0, 1, 2, 3. I got off. So if k is 3, 3 squared is 9 minus 1 is 8. And then if k is 4, I would have 15. So that I looked down and I got off. And I've got to keep going forever, right? So plus all the way to where k is equal to n, which would be n squared minus 1. That would be my last term in my series. Now this goes the other way. This gives us terms in our series and tells us to write the index of summation. Now notice that it doesn't keep going. It doesn't have the ellipsis, the dot, dot, dot. So I have 1, 2, 3, 4, 5 different terms. The thing that I see is changing is my denominator. It counts from 1 to 5. So that I'm going to assume that my index of summation, and we'll use k, goes from 1 to 5. So term 1, term 2, term 3, term 4, term 5, where my general term is 1 over k squared. That matches the pattern that I see given to me. Okay, last one on this page. Look at your terms. I'm going to 2n minus 1, so that lets me know that my index of summation is going to be infinite. So I'm going all the way to n. And I'm going to use a k here. So this gives me my clue about my general term. I'm assuming my general term is going to be 2k minus 1. What I need to know is, where do I start? Do I start with 0? Do I start with 1? Do I start with 2? Where do I start? Well, let's try 0. If I had 0, I would have a negative 1. That's not right. If I had 1, I have 2 minus 1 is 1. That one works. So there is my index of summation for that particular sequence. Okay, our last page of notes gives you a ton of information, guys. This is going to give you the set of properties and formulas of sequences. It's going to be kind of a cheat sheet. Now that we know some things about sequences and series, we're going to introduce these properties that will help you evaluate the sequences. So if you are asked to sum different types of sequences, it's going to let you know how to do that more quickly based on a pattern. So I'm going to fill these in for you. These are also found in your book, but we're going to fill these 8 patterns in and talk about them. 1, 2, 3, 4, 5, 6, 7, 8 different patterns that we're going to talk about. And then we're going to practice some down here at the bottom with these 4 practice activities. Our first pattern for our index of summation is c times a to the k. Now notice that my index of summation all go from 1 to n except for number 4, and it goes from j plus 1 to n, and so it's going to be a little bit more complex, but we're going to use it down at the bottom on D, so we'll talk about it down there. This first one, think about putting this in parentheses so that I'm multiplying some constant c times a to the k. If I'm going to sum that, I would take c times the first term, c times the second, plus c times the third, c times a to the third, and I go all the way to c times a to the n. Well, I can simplify that by factoring out the c. So I can think of it as just adding all of these and multiplying the sum times c, which means I can just pull that c out and find the sum of the values of k, a sub k, and then multiply that times c. To get to this, we are using our distributive property from arithmetic. Our distributive property from arithmetic. Okay, so for our second case, where we are adding 2 terms together and finding the sum of that, I can split that apart. And I can say, you know what, I can sum the first set of terms, and I can just add that to the sum of the second. I just add those together. This one and the next one are based on the commutative and associative properties of addition. So based on commutative and associative properties. The next one, I'm going to do the same thing except I'm subtracting. So I have sum from 1 to n of a sub k, and then I'm going to subtract from that the sum from 1 to n of b sub k. So those are just alike except one is adding, one is subtracting. Okay, let's look at this next one. I'm going to change colors just so we can kind of try to keep it lined out a little better. Okay, this one is a little bit more complicated. So notice that my index of summation is different. I'm going to find first of all the way of the sum from 1 to n. So from k equals 1 to n, I'm going to find that sum, and then I'm going to subtract from it the sum of 1 to j, those terms. And that works as long as j is greater than 0 and less than n. And this is helpful when we start. This is helpful when that index starts at some number greater than 1. If it doesn't start at 1, this one is really helpful. Okay, number 5. This is just, if c is a constant, if my term is a constant, I just do c times n. And this works as long as c is a real number. Just c times n. This is goes back to our definition of summation notation. If you're interested in looking up why we do that one that way. For number 6, 7, and 8, these proofs require induction. We are not going to talk about proving them right now. I'm just going to write it out. If you have k as the general term and you're summing from 1 to n, you're just adding 1 plus 2 plus 3 plus all the way down to n. That comes out to be n times n plus 1 divided by 2. That is the sum for that series. On number 7, where I'm adding up the k squared terms, that's the same thing as 1 squared plus 2 squared plus 3 squared all the way to n squared. To find that, I multiply n times n plus 1 times 2n plus 1, and I divide by 6. Again, the proof of this, why this works, is found in the book. We're not going to take the time to do that today. for this one where I'm cubing terms. So that's the same thing as 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed. That pattern is going to be a little bit more complex. It looks like this: n times n plus 1 over 2, n times n plus 1 over 2, but then I square that. So these last three we're not going to prove right now because the proofs require induction. Okay, we're just going to introduce them and use them to simplify our lives. So these are basically just shortcuts. They're used to simplify how we find sums for different types of series. Okay, so let's find our shortcut to help us out down here. For this first one, for A, we have the sum of k squared minus k. Well, based on number 3, I see that I can break that apart. So I have from k equals 1 to 10 k squared minus the sum of k equals 1 to 10 of k. And then I have, for this first term, this is k squared. So I'm going to go down here to number 7. And so you know what? I can just do this. I can do n plus 1, 2n plus 1. So that is going to be 10 times 11 times 21 all over 6, because that is the sum of that k squared term. And then I'm going to subtract that from that, the sum of k, and that shortcut is number 6. So I have 10 times 11 over 2. Well, when I plug that into my calculator, this first term gives me 385 minus the second sum is 55. So the sum of the original sequence is going to be 330. See how much easier that was than going through 1 to 10 and finding each of those terms, 10 terms, and adding them together. Okay, let's look at B. Again, we can split it apart using that third rule. So I have k equals 1 to 4 of 5k minus the sum k equals 1 to 4 of a1. Well, 5k, that sum, that looks like number 1. So that I can just do c times the sum of k, right? So I pull out that 5 and I say, you know what? 1 to 4 of k, that's right here, n times n plus 1 over 2. So that is going to be 4 times 5 over 2 times 5 minus, and then this is a constant, so that is number 5, 4 times 1. Well, here I've got 20 divided by 2 is 10 times 5 is 50 minus 4 is 46. So that's the sum of that series. All right, number C, not number C, letter C. We have to break it apart into 3 different pieces. We're using rule number 2, shortcut number 2, where I can add up the individual sums of the terms. So I'm going to start by rewriting it as from k is 1 to 20 for k squared plus the sum k 1 to 20 for 5k plus the sum of k from 1 to 20 for 2. So I have a squared term, I have 5 times a constant, or 5 times k, and then I have 2. For my squared term, I go back to number 7, where n is 20. So that gives me 20 times 21 times 41 all over 6. For the second one, I'm going to pull that 5 out front and multiply it times number 6 rule here, 20 times 21 over 2. And for this last one, I have 20 terms times 2 because they're all a constant. Alright, my first one, when I plug it in my calculator, I get 2,870 plus the second term sums to 1,050 plus 40 for a total sum of 3,960 for that sequence. That is so much quicker and easier than trying to find all 20 terms, combinations of that, and adding those all together. Alright, right here, this is where we have that index that does not start at 1. So this is where we are using the fourth rule. Here's what this is going to look like. First, we're going to pull this 3 out so that we have 3 times k equals 5 to 12 of k cubed. Now we are going to deal with the index like it tells us to on this first term. So 1 to n is going to be 1 to 12. So when I do this next step, I have 3 times the sum of k equals 1 to 12 of k cubed minus, because that's what it tells me to do, and then I go to j, so I go to 5. No, not to 5. 5 we want to include. We don't include the first 4. So the sum of k equals 1 to 4 of k cubed. Alright, moving on down. 3 times. Now this first parentheses, I'm summing k cubed from 1 to 12. My cubed pattern is here. So that is going to be 12 times 13 over 2 squared. And I'm subtracting from that 1 to 4, so k is 4, n is 4. 4 times 5 over 2 squared. Okay, so I have 3 times 6,084 minus 100, which is 3 times 5,984, which comes to a sum of 17,952. Now, I don't do all that in my head, obviously. I have it written down. Have your calculator handy, but make sure you can see how you can use those shortcuts.